Welcome to this coding problem walkthrough. Today, we'll be exploring a fascinating problem from the realm of string manipulation, problem number 161, one-edit distance. This problem challenges us to determine if two strings are exactly one edit away from each other. It's a great exercise for sharpening your skills in string analysis, edge case handling, and optimizing algorithms. Let's dive in. The problem asks us to determine if two strings, S and T, are exactly one edit distance apart. An edit refers to a single operation that can either insert a character into one of the strings, delete a character from one of the strings, or replace a character in one of the strings. If the two strings can be made equal with exactly one of these operations, we return true. Otherwise, we return false. The input to the problem consists of two strings, S and T, and the output is a Boolean value indicating whether they are one edit distance apart. Let's look at the first example to understand this better. If S is ab and T is ACB, we can insert the character C into S to make it equal to T, so the result in this case would be true. For the next example, we have S as cab and T as add. Here, the output is false because the strings differ by more than one edit distance. To transform S into T, we would need multiple operations, such as deleting C and replacing B with D. Since the problem requires that the strings differ by exactly one edit, this case does not satisfy the condition, and the result is false. These examples help illustrate the need to carefully evaluate the number of edits required to make the strings equal. Now, in the third example, S is 1203 and T is 1213. Here, we can see that the strings differ by only one character. By replacing the 0 in S with 1, the two strings become identical. Since this transformation requires exactly one edit, the output is true. The problem also specifies some constraints. The lengths of S and T are guaranteed to be between 1 and 10,000, and both strings consist only of lowercase English letters. These constraints ensure that we don't need to handle empty strings and that the inputs will always meet these criteria. There are also some important edge cases to consider. First, if S and T are identical, the output must be false because no edits are required, they are already equal. Another scenario is when the absolute length difference between S and T is greater than 1. In such cases, it is impossible to make the strings equal with just one edit, so the result must also be false. Finally, for strings with lengths close to the upper limit of 10,000, our solution must be efficient to avoid exceeding time limits. These considerations are crucial to ensure that our solution handles all possible cases correctly. To solve the problem of determining whether two strings are one edit distance apart, one approach we might consider is the brute force method. The intuition here is straightforward. We can generate all possible strings that are one edit away from the first string, S, by performing single character insertions, deletions, or replacements. Then, we check if any of these modified strings match the second string, T. Alternatively, we could generate all one-edit variants of T and compare them to S. In terms of implementation, this involves systematically enumerating all possible single-character edits for one of the strings and comparing each resulting string with the other. However, the complexity of this approach is a major drawback. For each edit type, we perform operations proportional to the length of the string, which results in a time complexity of O(n) squared in the worst case. Additionally, the space complexity is O(n), as we need to temporarily store the generated strings. While this method is conceptually simple, it quickly becomes impractical for longer strings due to its inefficiency. The brute force approach, while theoretically sound, is not suitable for larger strings because it involves a significant amount of redundant computation. This inefficiency makes it impractical for real-world scenarios where performance matters. To address this, we can consider a more optimized strategy, the two-pointer approach. The intuition behind this method is based on a key observation. If two strings are one edit distance apart, the difference in their lengths can only be 0 or 1. This means that if the strings differ in length by exactly one character, the shorter string should match the longer string when we skip one character in the longer string. On the other hand, if the strings are of equal length, there should be exactly one differing character. These constraints allow us to focus on a much smaller set of possibilities compared to the brute force method, making the two-pointer approach inherently more efficient. To implement the two-pointer approach, we start by comparing the lengths of the two strings, S and T. If the difference in their lengths is greater than 1, we can immediately return false because they cannot be one edit distance apart. Next, we use two pointers, I and j, to traverse the strings. If the characters at the current positions of the pointers match, we simply move both pointers forward. However, if the characters differ, we need to make a decision. If the strings are of the same length, we skip one character in both strings, essentially simulating a replacement. If one string is longer, we skip a character in the longer string only, simulating an insertion or deletion. Throughout this process, we ensure that no more than one edit is made. Once the traversal is complete, we also account for the possibility of one additional character remaining in the longer string, which would still qualify as a valid one edit difference. This implementation achieves a time complexity of O(n), where n is the length of the shorter string, and it uses O(1) space, as no additional data structures are required. When comparing the two approaches, it's clear that the brute force method, while exhaustive, is computationally expensive and unsuitable for larger strings. It explores all possibilities without leveraging the constraints of the problem, leading to significant inefficiency. In contrast, the two-pointer approach is designed to take advantage of the problem's structure. By focusing on the constraints, such as the limited length difference and the allowance of only one edit, it avoids unnecessary work and provides a streamlined solution. This makes the two-pointer approach far more efficient. In fact, it is the chosen strategy for this problem due to its simplicity, clarity, and optimal performance. It achieves linear time complexity while remaining easy to implement and debug, which are critical factors in scenarios like coding interviews or competitive programming. Key observations that drive this method include the fact that the length difference dictates the type of edit and that at most one mismatch or skipped character is permitted. These insights ensure that the solution is both effective and efficient. The two-pointer approach does come with certain trade-offs. Specifically, it assumes that the strings are traversed in order, which means it cannot handle unordered or non-contiguous edits. However, this limitation is irrelevant for the current problem, as the definition of one edit distance explicitly requires edits to be contiguous and limited to a single operation. In summary, the two-pointer approach is both efficient and elegant. It provides an optimal O(n) solution while adhering to the problem's constraints. By leveraging the structural properties of the strings and ensuring minimal overhead, this method strikes the perfect balance between performance and simplicity, making it the ideal choice for addressing this problem. The problem is to determine if two strings, S and T, are exactly one edit apart. An edit can be an insertion, a deletion, or a replacement of a single character. This means we need to check if we can convert S to T using exactly one of these operations. To solve this efficiently, we use a two-pointer greedy approach, which avoids the inefficiencies of brute force methods that generate all possible edits. The first step in our algorithm is to calculate the lengths of both strings. If the absolute difference between their lengths is greater than 1, we can immediately return false because a one-edit transformation is impossible. Next, we identify the shorter string. If S is longer than T, we swap them. This ensures that we always handle insertions and deletions consistently, simplifying the rest of our logic. With the shorter string identified, we initialize two pointers, I for S and J for T, both starting at the beginning of their respective strings. We also introduce a Boolean flag, found_difference, which will help us track if we've already encountered a mismatch. Using these pointers, we traverse both strings character by character. If the characters at the current positions match, we simply move both pointers forward. However, if the characters differ, we check if found_difference is already set to true. If it is, we return false because this would mean there's more than one mismatch. Otherwise, we set found_difference to true and handle the mismatch based on the length difference. For replacement, we increment both pointers. For insertion in T, we only increment J. For deletion in S, we only increment I. This ensures that we handle all possible edit scenarios efficiently. After traversing the strings, we need to account for any remaining characters in either string. If one pointer hasn't reached the end, we check if the remaining characters in the longer string are exactly 1. If not, we return false. Otherwise, we return true because all conditions for a valid one-edit transformation are satisfied. This approach leverages the efficiency of a greedy traversal, ensuring that we only scan the strings once. By always treating S as the shorter string, we simplify the logic for handling insertions and deletions. The found_difference flag enforces the one-edit constraint by allowing only one mismatch during traversal. This algorithm achieves a time complexity of O(n), where n is the length of the longer string, and a space complexity of O(1), as we only use pointers and a Boolean flag for additional storage. When solving this problem, it's important to consider edge cases. For instance, if both strings are empty, they are not one edit apart, so we return false. If only one string is empty, they are one edit apart only if the other string has a length of 1. For single-character strings, we handle all possible edits explicitly: insertions, deletions, and replacements. If the strings are identical, meaning S equals T, no edits are needed, so we return false. Finally, for strings where the length difference is greater than 1, we can immediately conclude that they are not one edit apart, as this case was already filtered out in the first step of our algorithm. These edge cases ensure that our solution is robust and handles all possible inputs correctly. To understand this algorithm better, let's walk through a few examples. In the first example, S is ABC and T is AB. The length difference is 1, so the strings are valid candidates for a one-edit transformation. As we traverse, the first two characters match, so we increment both pointers. At the last character, S has C while T has no corresponding character. This represents a valid deletion, so we return true. In the second example, S is ABC and T is ADC. The lengths are equal, so we check for a replacement. The first characters match, but the second characters differ. We set found_difference to true, then continue. The last characters match, so we return true for a valid replacement. In the third example, S is ABC and T is ABCD. The length difference is 1, and as we traverse, all characters in S match their counterparts in T. The extra character D in T represents a valid insertion, so we return true. Now, let's look at the code implementation. The function isOneEditDistance starts by calculating the lengths of S and T. If the absolute length difference is greater than 1, the function immediately returns false. Next, we ensure S is the shorter string by swapping them if necessary. We then initialize two pointers, I and j, and a Boolean flag, found_difference. As we traverse both strings, we compare the characters at the current positions. If they match, we move both pointers. If they differ and found_difference is already true, we return false. Otherwise, we set found_difference to true and handle the mismatch based on the length difference. After the loop, we account for any remaining characters in T and return the result. This implementation is efficient, concise, and handles all edge cases effectively. This solution determines if two strings, S and T, are exactly one edit distance apart. The three possible edits are insert, delete, or replace one character. Here's the line-by-line breakdown. 1. Length check. The first condition checks if the absolute difference in lengths of S and T exceeds 1. If so, the strings cannot be one edit apart, and we return false immediately. 2. Order adjustment. To simplify logic, we ensure that S is the shorter string, or equal in length. This allows us to handle cases consistently where one string might be longer. 3. Mismatch detection. Using a for loop, we iterate through both strings. At each index, we compare characters. The first mismatch indicates where an edit might be needed. If the strings are of equal length, the only valid edit is replacing the mismatched character. This is checked by comparing the remaining substrings after skipping one character in both S and T. If the strings have unequal lengths, the only valid edit is inserting one character in S, or equivalently deleting one character in T. This is checked by comparing the remaining substring of S with the substring of T starting from the next character. For edge case, if the loop completes without finding any mismatch, the strings are identical except for a possible extra character at the end of T. This is checked by confirming that T has exactly one more character than S. The algorithm is efficient, with a time complexity of O(n), where n is the length of the shorter string. It handles all edge cases, including empty strings and strings of varying lengths. The logic ensures correctness by directly verifying the conditions for exactly one edit distance. Here, we begin the Java implementation of the one-edit-distance problem. The method isOneEditDistance takes two strings, s and t, as input and determines if they are one edit apart. The first step is to check if the absolute difference in their lengths is greater than 1. If it is, we can directly return false, as the two strings would require more than one edit to become the same. Next, we ensure that s is the shorter string, or they are of equal length. This simplifies the logic later on, as we can focus on the shorter string for comparisons. If s is longer, we swap the two strings. Then, we iterate through the characters of s to find the first mismatch. Once a mismatch is found, we handle two scenarios. If the strings are of equal length, we check if replacing the mismatched character in s with the corresponding character in t makes the remaining substrings identical. If the strings are of different lengths, we check if skipping the mismatched character in the longer string, t, makes the remaining substrings identical. If no mismatch is found during the iteration, we still need to account for the possibility that the strings are one edit apart because the longer string has one additional character at the end. This is checked by ensuring that the length of t is exactly one more than the length of s. If this condition is satisfied, the strings are indeed one edit apart. Otherwise, they are not. This completes the implementation of the method. To solve the problem, we start with the first example where the input strings are s equals abc and t equals ab. First, we calculate the length difference. The length of s is 3, and the length of t is 2, so the absolute difference is 1. Since the difference is within the allowable range of 1, we can proceed to the next step. Here, we ensure that s is the shorter string. Since s is longer than t, we swap the two strings. Now, s becomes ab and t becomes abc. Next, we iterate through the strings to find the first mismatch. We compare the characters at index 0, s 0, and t 0, are both a, so there's no mismatch. Then, we compare the characters at index 1, s 1, and t 1, are both b, so again, there's no mismatch. After finishing the loop, we check if t has exactly one extra character at the end. Since the length of s plus 1 equals the length of t, 2 plus 1 is equal to 3, the strings are one edit apart. The output for this example is true. In the second example, the input strings are s equals abc and t equals adc. First, we check the length difference. Both strings have a length of 3, so the absolute difference is 0, and we can proceed. Next, we ensure that s is the shorter string. Since the lengths are equal, no swap is needed, so s remains abc and t remains adc. Now, we iterate through the strings to find the first mismatch. At index 0, s 0, and t 0, are both a, so there's no mismatch. At index 1, s 1, is b, and t 1, is d, which gives us a mismatch at this position. Since the lengths of s and t are the same, we need to check the replacement condition. This involves verifying if replacing s1 with t1 results in the remaining substrings aligning. The substrings from index 2 onward are s2 smiley face equals c and t2 smiley face equals c, which match. Therefore, the replacement condition is satisfied, and the output for this example is true. Now, let's look at the third example where the input strings are s equals abc and t equals abcdf. First, we check the length difference. The length of s is 3, and the length of t is 6. The absolute difference here is 3, which exceeds the allowable range of 1. Since the length difference is too large, it's impossible for the strings to be one edit apart. As a result, we immediately return false for this example. The final output is false. Here, we analyze the time complexity of the solution in detail. First, the length difference check involves calculating the absolute difference between the lengths of the strings s and t. This is a simple operation that takes constant time, or O1, since it only involves comparing integers. Next, swapping the strings based on their lengths also takes O1. Instead of copying or rearranging the strings, we simply swap their references, which is an instantaneous operation. The main loop then iterates through the characters of the shorter string s. If n is the length of s and m is the length of t, the loop runs for up to n iterations, making its contribution O(n) in the worst case. This step forms the backbone of the overall time complexity. Now, we consider the cost of substring comparisons, which occur when we encounter a mismatch during the main loop. Substring slicing and comparison together take O, k, where k is the length of the substring being examined. Since k is bounded by the lengths of s or t, this operation contributes O, n, at most. Lastly, the final length check, which ensures that len, s, plus 1 equals len, t, is a simple arithmetic operation that takes constant time, or O1. When we sum up all these contributions, the dominant terms are the loop and the substring comparison, both of which are O, n. Thus, the total time complexity of this optimized solution is O, n, where n is the length of the shorter string. Turning to space complexity, the analysis is straightforward. The given strings s and t are part of the input and do not add to additional memory usage. When we swap the strings based on their lengths, no new memory is allocated because only the references are swapped, making this step O1. However, substring slicing during mismatch checks introduces some additional memory usage. Each sliced substring creates a new string in memory, which takes O, k, space, where k is the length of the substring. Since the maximum possible length of any substring is limited by n, the length of the shorter string, the space complexity for slicing is O, n. Altogether, this makes the total space complexity O, n, in the worst case. Summarizing the space complexity, the overall additional memory usage comes from substring slicing, which is bounded by the length of the shorter string. Therefore, the total space complexity is O, n. To put this in perspective, consider a brute force approach. In that case, we might generate all possible edits, such as insertions, deletions, or replacements, and check if one matches the target string. This would result in a time complexity of O, n squared, as each edit operation takes O, n, and there could be up to O, n, such operations. The space complexity would also balloon to O, n squared, because storing all possible edits requires significant additional memory. In contrast, our optimized solution avoids unnecessary operations and limits memory usage. With a single pass through the shorter string and efficient substring handling, both the time and space complexities are reduced to O, n, making it far more efficient. Finally, let's break down the best, average, and worst cases for this solution. In the best case, if the lengths of s and t differ by more than 1, the function can exit early, taking only O1 time. This happens because the length difference check immediately rules out the possibility of the strings being one edit apart. For the average case, the loop typically runs until the first mismatch is found, at which point a substring comparison is performed. This results in a time complexity of O, n. In the worst case, the strings might be nearly identical except for one edit near the end. Here, the loop has to iterate through almost all characters, and the substring comparison also contributes O, n. Despite these variations, the overall time complexity is consistently O, n, across all cases, with the only difference being the constants involved depending on the input characteristics. When solving the one-edit distance problem, there are a few common mistakes to watch out for. First, ignoring edge cases like empty strings can lead to unexpected errors. It's important to remember that inputs where one or both strings are empty are valid and must be explicitly handled. Make sure your solution accounts for cases like this up front. Next, overlooking the one-edit condition is another frequent mistake. The problem strictly limits you to a single edit, whether it's an insert, delete, or replace, so allowing more than one edit, or failing to return false when multiple edits occur, directly violates the requirements. A good way to address this is by using a flag or counter to track edits. Lastly, incorrect index handling during comparisons can cause issues. For example, after making an edit, you might lose track of indices, leading to infinite loops or incorrect results. To fix this, carefully adjust your indices after each operation and document your pointer movements clearly in your code for better readability and accuracy. Another common pitfall is relying on inefficient brute force implementations. For example, generating all possible one-edit variations of a string and then comparing them can significantly increase time complexity, often to O, n squared, or worse. This approach becomes impractical for large inputs, so it's better to use a direct comparison method that's more efficient. Additionally, assuming that a string length difference greater than 1 always fails can also lead to mistakes. While it's true that lengths differing by more than 1 cannot be one edit apart, you must still handle cases where the lengths are equal, as a replace operation is possible in those scenarios. The best way to avoid this mistake is to implement separate logic for each operation: insert, delete, and replace, and test your solution thoroughly with examples that cover all possibilities. To perform well in an interview setting, there are some key insights to keep in mind. First, make sure you fully understand the definition of one edit. Confirm with the interviewer what counts as an edit, such as whether it includes only insert, delete, and replace. This ensures your solution aligns with the problem's requirements. For unequal string lengths, a two-pointer pattern is a highly effective strategy. It allows you to traverse both strings efficiently while keeping track of edits. Additionally, optimize your solution for an early exit. If you detect more than one edit, there's no need to continue the comparison. Exiting early can save significant time. Pay close attention to edge cases too, like when the strings are empty, consist of a single character, or are already identical. Lastly, clearly explain your approach to the interviewer, highlighting the trade-offs between brute force and optimized solutions. This demonstrates your understanding of both time complexity and problem-solving strategies. The one edit distance problem is closely related to several other problems in LeetCode that you might find useful to study. For example, LeetCode 72, edit distance, is a generalization of this problem and involves finding the minimum number of edits to make two strings equal. Similarly, LeetCode 68, text justification, and LeetCode 186, reverse words in a string 2, involve string manipulation and can help you sharpen your skills in handling edge cases and optimizing solutions. When considering alternative approaches to solving the one edit distance problem, brute force is one option. This involves generating all possible one-edit variants of the first string and checking if any of them match the second string. While this method is simple to understand, it is computationally expensive and unsuitable for larger inputs. A more efficient alternative is the two-pointer approach, which lets you traverse both strings while allowing for a single edit. This method is much faster, running in O(n) time for most cases, though it requires careful handling of indices to avoid errors. For more advanced variants of the problem, dynamic programming can be a powerful tool. In these cases, you use a DP table to compute the minimum number of edits needed to make two strings equal. This approach is especially useful for problems like LeetCode 72, where you need to minimize edit distance across multiple operations. However, for the one edit distance problem, dynamic programming is often overkill. While it provides a general framework for solving string edit problems, its time complexity of O(n)(m) makes it less efficient than simpler approaches like the two-pointer method for this specific case. Understanding when to apply dynamic programming and when to use a simpler solution is a valuable skill, especially when balancing efficiency and complexity in your code. Great job making it to the end. In this session, we tackled the one edit distance problem, starting with a brute force approach to explore potential solutions. Key takeaways include understanding the concept of one edit distance and how to handle edge cases effectively. Remember, practice makes perfect, so keep solving similar problems to refine your skills. Thanks for watching, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!